Hey, welcome everybody. Just getting my pen to work here. All right, this is 7C, rationalising the denominator when you have surds in a denominator of a fraction. Now, let's just look at something simpler first. If you had 1 on root 2, so in ye olden days, it was a bit difficult to deal with surds in denominators. So you might want to rationalise that. This is an irrational number. I can multiply by the same surd. Effectively, I'm just timesing by 1. I'm keeping the fraction the same. And we times the top times the bottom. Root 2 times root 2 is just 2. And this way we have the identical fraction here, but without the irrational number in the denominator. Some people find it, some people, just interestingly, find it a bit hard to go between fractions in these forms. If I had something like this, and I wanted to go in the other direction, maybe I could see that that 3 could be thought of as root 3 times root 3, and then they would cancel out, and I'd get 1 on root 3. So with a bit of practice, you can see that this pattern fairly easily, and these are nice simple fractions. But the book jumps into these denominators with 2 parts. And the way that we rationalize the denominator here, it's a really nice technique, which does actually come up in future mathematics, certainly in the Year 12 methods course that I'm teaching at the moment. It can be a bit difficult to solve algebraic expressions when variables are tucked away in surds. So for example, if I had something like this, and I'm trying to find out what x is, it's quite hard to figure it out in a satisfactory way when it's hidden away in the surd. So we can use a technique with surds, and it's basically just a difference of 2 squares. We multiply it by a conjugate. So in Year 10, you learnt this. And what does this equal? Well, if I did the whole expansion of this binomial product, I would get minus AB plus AB. You should already know this, guys. These cancel out. So whenever we see this plus minus pattern in the binomial product, we get a squared minus b squared. Okay, and we've got the same thing happening, without variables, without the alphabet getting involved. But if I took this one here, I've got root 2 minus 3. Well, if I multiplied that by root 2 plus 3, I'll get rid of all the surds. Okay, we'll have the first term, so this is like my a term. I've got an a minus b. So the first term is representative of an a term, it's a root 2. And I've multiplied this by its conjugate term. And by conjugate, we mean change a minus to a plus or a plus to a minus. In this case, we had a minus between the a and the b term. So I've multiplied by the same thing but with a plus. All right, we know that this will give a squared minus b squared. And over here we'll get root 2 squared, which is 2, minus 3 squared, minus 9, which equals minus 7. So now we've gotten rid of the surds. Okay, so that's the technique that we're using, and it's quite useful. With a fraction, you can do anything to a fraction as long as you do it to the top and the bottom. So with this example here, I would have to be, let's see how good this pen is. I'd have to multiply the top as well by root 2 plus 3, as well as the bottom. Right? As long as you, sorry, that's not good. Try that again. That should be a plus. So as long as you times top and bottom of a fraction by the same thing, the fraction doesn't change, right? This is simply just the idea that, you know, something like this. These two fractions are identical, even though this one, you know, to get to 2 on 4, you've times top and bottom by 2, right? Okay, so let's pick one at random. I don't know, maybe this one here. Right, so root 2 all over root 2 minus 5, and the goal is to get rid of all surds out of the denominator. So we multiply by the conjugate of that denominator. All right, now on top, we're going to have root 2 times root 2, which is 2, plus root 2 times 5, which is 5 root 2. So we'd have 2 plus 5 root 2 on the top of the fraction. And on the bottom, we've got our a minus b, a plus b pattern. So we've got root 2 times root 2 is 2. Minus 5 times 5 is minus 25. And so this part here will equal minus 23. Now I'd probably write the answer just with a big minus out the front of it. Although it'd be fine to leave the minus on that 23. Just for all intents and purposes, right, these three fractions which I'm writing here are effectively the same. I mean, they're not identical, but when I go to use them in mathematical equations, they're effectively going to be the same thing. Of course, this is different when I have a minus, but if you know, that will equal plus, because you have a minus term divided by a minus term, which is positive. But if you think, maybe if you think of the fractions as division, if you're doing a division of a divide b and one of those is minus, then the whole thing is minus, right? To be strictly correct, there is a difference between a negative symbol and a minus sign. Your calculator makes that distinction. Let's show you. Because you have a unary operator, your calculator has a separate button for the negative symbol, whereas the minus, you know, it looks slightly different. It's a bit bigger, slightly lower. So there's a negative one and there's a minus one. So mathematically there are different symbols, but most of the time we don't really need to worry about the difference. Okay, I think I'll stop it there, and then we'll the next video will show you a few more worked examples of 7C.